Good morning, everyone. It's wonderful to see you all again, and also a warm welcome to those joining for the first time. This is only our second session of Reward Loop, and it already feels like we are building the kind of learning community we dreamed of, a place where people passionate about reinforcement learning, robotics, and control come together to share their ideas, discuss breakthroughs, and stay inspired. When we started Reward Loop, our aim was simple to create a space where we can keep pace with the rapid progress in these fields, not in isolation, but together. Reading papers and exploring new techniques on our own can be exciting, but the real growth comes from discussion, from asking questions, and from seeking how different minds approach the same challenge. That is exactly the spirit of this group. Our first talk set the tone beautifully, and today we continue that journey with a topic that captures the imagination of anyone working in robotics: legged locomotion. Quadruped robots are no longer science fiction. In recent years, we have seen incredible advances: robots that can run, climb, and adapt to challenging terrain. But achieving this level of agility is far from trivial. Reinforcement learning has been a driving force behind many of these breakthroughs. Yet, taking policies from simulation to real hardware still remains a huge challenge. To walk us through the key milestones from policy optimization and domain randomization to rapid motor adaptation, and to highlight the open problems that still keep researchers busy, we have with us Mr. Vishwanath R. Vishwanath will be speaking on learning for legged locomotion, progress and challenges, focusing on quadrupeds. Please join me in giving him a warm welcome as we dive into the exciting frontier of robotics. Thank you. Over to Vishnu.
Uh, Good morning to everybody. So thank you for joining to this talk. I'm Vishwanath R, master student in robotics and mobility systems at IIT Jodhpur. So today I'll be talking about an interesting topic called learning for legged locomotion, focusing on the progress and challenges mainly in four-legged robots called quadrupeds. So we'll have a very basic overview of how the field of quadruped robots progressed from classic control to reinforcement learning, and how far are we from a truly generalized legged locomotion. So why locomotion first? Why did they had to take the problem of locomotion? So if you take any application in robotics, the fundamental skill for all the robots is to move from one point to another point, which is to perform locomotion. With good locomotion, you can achieve various applications which are used in daily life, such as exploration, inspection, etc. But then, when we do have wheeled robots, and when we can try solving the problems of locomotion with wheeled, why did we have to focus more on legged, and what makes legged much harder than wheel locomotion is what we'll be discussing throughout the talk. So one of the reasons why legged robots became famous in the field is that legged robots gave us an opportunity to explore and exploit those applications where it is hard for chained or mobile robots to go, which is the same as what we as humans and animals are capable of. And one more reason is that because of such systems, the control of such legged robots is much harder than wheeled robots, because in a much simpler way, you can always reduce the contact dynamics of wheel mobile robots into a very less number of points, whereas in legged locomotion you always have a uh, contact rich dynamics for the locomotion part. So trying to solve this problem with reinforcement learning, as we would see, would also come up to be one of the benchmarking task for reinforcement learning. And I have gathered few videos of famous legged robot progresses. So the first one is MIT's Mini Cheetah, which every one of us would have seen. Uh, this was this was one of the pivotal advancements in legged robot research space. So what video you see here is a reinforcement learning based training policy, which actually enabled the cheetah to achieve velocities which are higher than what people were able to achieve with traditional controllers. And the second video is from IIT Zurich. This is also a reinforcement learning based training policy on their own robot. One thing that you could be observing is that the morphology of the robot is not exactly the same, but still reinforcement learning for that particular robot was good enough to learn it. And the third video is from Indian Institute of Sciences, Bengaluru. So this is also a locomotion policy trained using reinforcement learning on two different quadrupeds. So, but before going to reinforcement learning based approaches, first we have to know how legged robots were controlled earlier, because before going into RL, why do we have to go into RL if classical controls are good enough? So, of course, the research of legged robots is believed to, have started with the great Professor Mark Reibert, who did a lot of research on legged robots and wrote a book called Legged Robots That Balance. So he did a research on Hopper robot and tried to come up with the template dynamics using your slip model and all those classic control theories. So the issue with even though these classic control methods proved to be very good back in those days, the major issue was these were all hand designed and hand tuned. So every time you want this control to be running, you had to make sure that you spend very good amount of time tuning the robot, making sure that it is good enough to adapt to the current task. And of course, this hand tuning comes at a cost of generalization to new environment or new terrains. And if you see, fundamentally, the classic control always had a modular controller design approach. So basically, you can boil this down to something of two elements. The higher level element will try to plan on how the on what trajectory should be followed, and the lower level element in the classic control method would execute on how the trajectory should be followed. So it was basically two controllers trying to match each other's task. And one of the most earlier classic control, which is technically no control. This is called a passive dynamic walker, which walks using just the gravity, which just exploits gravity on a simple inclined plane. And this was one good theory that demonstrated on how legged robots could exploit such forces available to navigate. And talking about this template dynamics, which is like a very essential point for classic control method, for running it used something called slip model, which I had already mentioned, called spring loaded inverted pendulum. So these model gave not the accurate dynamics, but an approximate dynamics of how the robot could perform locomotion. And since this was approximate, this did come at a cost of task specific tuning. And even though they were robust in a very controlled environment, they were always brittle when you try to give them a redesign or when you show them new terrains. Coming to the RL foundation for locomotion. So with these in perspective, control methods such as PAD based, MPC based in perspective, RL in locomotion entered with the advancements in algorithm. So the first breakthrough so the main issue was, even though DQ and DQ networks showed a big breakthrough in the RL space, it was very good in Atari games, but the action space in Atari games are discrete. For control of locomotion task in Lego robots, it's not a discrete domain problem, it's a continuous domain problem. Hence, still we couldn't take these algorithms and apply them in locomotion tasks. So, requiring continuous control, the first algorithm which came up with a fairly good solution for it was DDPG, Deep Deterministic Policy Gradient Algorithm. But the issue was that it was very sensitive to hyperparameters. So they were one of the first papers to benchmark the algorithm on a locomotion environment, a 2D locomotion environment called Mujoko. So Mujoko is a simulator where this Hopper and Cheetah are the two available legged environments back in the time of DDPG paper, and they tried to show that DDPG was good enough to solve such continuous tasks. But still, being sensitive to hyperparameters, this was later fine-tuned as TRPO, where they will constrain the way your policy is being updated into a smaller region, which really showed stable learning and, of course, success on the same Mojoko environment. But still, the policy was improved. The algorithm was improved, and we reached PPO, proximal policy optimization, where apart from constraining the policy update to a smaller region, we also did clip the objective function, which showed a better performance in longer horizon task, and hence this became a standard baseline for locomotion tasks these days. Most of the papers that we come across these days would have PPO as their recipe. And as you can see here, this is an excerpt from the paper. These are the benchmarks of various algorithms until PPO on different Mujoko environment. And you could see that half cheetah, hopper, inverted double pendulum, these are all continuous control tasks. And you could see PPO, clipped PPO had performed much better than all the other environments for the same number of training time steps. So now at this point what happened was, now that we have a good enough algorithm for longer horizon task and continuous control, locomotion became a problem like what ImageNet was to deep learning. How ImageNet was a breakthrough in deep learning, and solving ImageNet was one of the benchmark tasks in deep learning field. Locomotion became the same for RL back then. So everybody wanted to come up with equally good or better controller for legged locomotion compared to the already existing MPC based model predictive control based approaches. So the early successes of legged locomotion was restricted only to simulation, and of course this was also demonstrated in all those papers that I have shown you before. And one big breakthrough happened by Deep Mimic. So what they tried to do is, rather than simulating the algorithms in a 2D environment, they came up to a 3D environment and showed that PPO was good enough to learn flips, power car, and acrobatics in the simulation. Yeah, and remember, this is only in simulation. We didn't shift to real robots yet. And probably one reason why we couldn't shift to real robots was because people started realizing that what if the algorithms are trying to exploit the quirks in the simulation, like the shortcuts in the simulation, which might not be true in real world. And this is one of the video of Deep Mimic, where they have shown that locomotion was successful in a 3D simulation environment. And you can see here, this is a very basic model of Mojoko's whole quadruped. And notice one more thing, that all the demonstrations shown in these videos do not show us any real robot. All these videos are ran a very rough estimates of how humanoids and quadrupeds could be. And if you see what the policy had came up with as a walking might not seem natural to, and hence this itself showed a clear statement that the policies that emerged out of the simulation environment did solve the problem, but they were not good enough to be transferred to real life. And so now we'll discuss why there was an issue while going from simulation to reality. So this is called a sim to real gap. This is one of the most famous hurdle for applying RL to locomotion, and probably to a good level of extent this still exists. So sim to real is basically the mismatch between what you see in your simulator and what you see in your lab. So you training your policy in a simulator, showing the same state and getting some actions. And if you try to implement the same policy on a physical hardware, and you would see that like there are videos also which I'll show in later part of slides where a direct transfer of sim trained policy or a raw recipe would fail in the real robot. So why does this happen? Why do we get success in simulation but not in the real world? One of the main reasons is that back then, even now to some extent, all the physics engines that we have do not represent real world dynamics. They simplify friction, they simplify impacts, they do not model actuator dynamics. It's hard for you to like as an innate property, it is hard for the simulator to contain backlash and all those problems that we face in actuators. And hence, whatever actions that happens in the simulator is close to a imaginary world dynamics. And one more point is that real world signals are noisier than clean sim states. This is more of like in real life, let's say when you have sensors, let's say you have an IMU in your robot, the signals that you get from those sensors, even after filters, do contain few amount of negligible noises, but simulators are imaginary clean environments where everything seems perfect. So what happens is that these policies, the learned policies, would always exploit these unrealistically precise dynamics, and it would when it goes to the real world, it would try to expect the same amount of reality which it had got in the simulation, and hence it would fail. And one more problem is that in real life there's always a time gap, a latency between the action that you take and the data that you receive, the observation that you get to the policy. But in simulation, this is all technically happening at the same time instant. And when you try to model this also in the real robot, you would see that the policy fails terribly. So as a result, policies that look great in the simulation, there was a very good chance that they would always completely fail on the hardware, and sometimes it would be in a very bad way too. So this fragile thing motivated researchers to find out transfer strategies which might ensure that the sim to real gap is at least minimal rather than negligible. And one such famous paper is called sim to real, and they tried addressing all these issues. So one of the foundational papers is sim to real, and what they did is that they have stated that the reality gap is caused by the model discrepancy between the simulated and real physical system. And what they mean by model discrepancy, it's not just the way it is modeled in your MJCF file or the simulated environment. It is also about the physics engine itself and the physics variables in the physics engines which cause this discrepancy. And this gap, since being a continuous control task, this gap becomes even worse as it is being amplified in the locomotion task. So how did they come up with a solution to solve sim to real? So one first thing that they did was called domain randomization. So one way to make sure that the simulation matches with reality is that why not, instead of having a perfectly good physical parameters, why not we sample the physical parameters with some amount of error? So the table that you see here is an excerpt from the paper where the authors trained the policy with random simulation physics. Like you can see here, the mass is not perfect 100%, it's plus minus 20%. And you can see motor friction varies, the inertia varies, the strength of the motor varies, and the control step. This control step variable and the latency variable is how they introduced the latency issue that we have discussed earlier, and contact friction, IMU noise. And by performing such domain randomization, they have shown us that locomotion RL in locomotion is not a hard recipe with good amount of domain randomization. And this video they have demonstrated the same. So now they are trying to learn it from scratch without any latency actuator model or domain randomization. And yes, it works pretty perfectly inside Mojoko. And this is what I meant by it fails terribly inside real world. Here you can see that with a little bit of improvement in the simulator, not in the physics engine, but in the parameters using which the physics engine would calculate dynamics, they were able to show that they could pretty much approximate what the real world dynamics could be, not would be, could be, with such techniques. And after domain randomization came a lot of techniques which gave us a robust real world locomotion. There are a lot of techniques, and I did mention three most famous techniques that is being used till today, and those are privileged learning, massive parallel simulation, and hybrid approaches. So first, let's talk about massive parallel simulation. This is something that we all can understand and relate very easily. So with GPUs, with the emergence of good GPUs and good GPU-based simulators like NVIDIA's ISAC Gym and ISAC Sim, researchers found that you can run thousands of environments parallelly, making sure that the policies can now explore more at the same time. And things that used to take days to train now can actually be achieved in minutes, which will make the learning and iterations much faster. So this massively parallel simulation gave us a very good roadmap on how fast and how easily we could learn to come up with good policies, so that we have greater amount of time focusing on how to solve the task rather than waiting for if the task is being solved with the hardware that we do have or not. And second most famous method is privileged learning. So privileged learning derives its idea from knowledge distillation in deep learning. And to keep it in a very simple way, so privileged learning is where you make sure that the simulation is different from real world. And what I mean by that is the policy that you train in the simulation will learn from every single data available in the simulation: terrain information, joint position, joint velocities, which are also available in real life, but things like terrain informations are not something that you get, that which is not easier to directly get in real life. And hence what you would do is that in simulation you would learn a policy, and that will serve as your teacher policy. And with a similar observable states in real life, you will train another student policy, and this student policy will come up with an action. Now we will try to regress between both of the teacher's actions and student action to make sure that the knowledge of the teacher is being transferred into the extra information that we learn from the teacher is being transferred into the real world. And one of the most famous extra informations that you exploit in the simulation are contact forces and terrain information. Because in real life, let's say if you had to incorporate contact sensors and everything, it would add on it would add on to the uh, physical connections and complexity of the robot, and two, estimating them and processing them would also add on to the latency in the real robot, and hence people prefer to exploit those property in the simulation and then distill the knowledge to student policies. And when you deploy these student policies, the states that this policy observes will not include those privileged information that you would have gotten in simulators, and hence it was very practical for you to learn the policy only with the current available states. And one more method of how privileged learning worked, which we will see in the further slides, used something called as latent variable, an idea that came from encoders and decoders from deep learning. And this idea came from a fact that what if I reduce this higher dimensional data that I have into a lower dimensional data, and in real life, what if I have an estimator which will estimate this latent variable, and the estimate of the latent variable could give me a comparatively fair guess of an action that I could take in real life, which would have exploited the data which was available in simulation. So it's basically like saying, I know all these things and I have a list of these are the possible states. And let's say you have a state now. If you can approximate the state into the state I have in the list, I will give you the action that you should take so that you wouldn't fail. So that you would achieve the task that you want to achieve. This is the fundamental idea of latent representation of environments. And the third method is a hybrid approach. So hybrid approach is a very interesting way, and basically most of the fundamental papers that you would read were all hybrid approaches, where we already knew that traditional controllers were good enough to take care of the trajectory optimization in the robots. So all our policies did were to learn a fair element or fair variable, like let's say joint position, joint velocity, or torque, and it is the duty of the control system present underneath to make sure that those variables are being achieved. So instead of throwing away classic control, researchers thought that what if we could add RL, reinforcement learning, in the top as a residual, so that base controller will always guarantee safety and stability, but RL will learn to improve your agility and adaptability, making sure that you get advantage of both the worlds. And this is video of massively parallel deep RL, which we discussed about exploiting GPUs. So the authors showed that massively parallel simulations in good GPU simulations like Isaac Gym, you could learn to walk in minutes when you have enough randomizations and terrain complexities. And this is very important because it reduces your iteration time, training time, making tasks which are achievable much more practical. And it also tries to give opportunities for us to explore rapidly adapting policies or scale experiments which wouldn't be feasible without exploiting GPU capabilities. So this was one key enabler for recent advancements, and what we could see here is a really robust policy which is helping the animal quadruped navigate the terrain. And this was not only constrained to four-legged locomotion, they have also shown Casey, the biped robot, training in the simulation worlds. and this was later deployed into the real robot and tested, and we could see that it's fairly pretty good. And most of the policies that you see in these videos are not exteroceptive, which means it's not that all of these policies exploit your vision data or your LiDAR data. Some of these policies are even proprioceptive, and they do rely only on intrinsic variables like your torque, position, velocity, IMU data, all those things that is not required from an external sensor. Yes. Talking about the recent advancements, one of the good emerging policies that came out after such GPUs being available was generalist policy. And note that by generalist policy, I don't mean a completely generalist policy for four-legged robot. These policies are such policies which are good enough to perform multiple gaits, let's say trotting, galloping, walking, all in one policy, or let's say multiple terrains. So this was one recent advancements in legged robots. The second is hierarchical RL, where this is one more area of research where you have higher level gate planners, higher level RL modules, which will plan what your gate pattern should be, and lower level modules which will try to exploit the available dynamics to achieve those gates in much efficient ways. And the hybrid controllers are what we discussed, using RL with, let's say, soft PD controllers where you will have lower KPKD values so that you could compensate for the perturbations that you get. And last thing is open source, not just open source simulators, it is just the open source community in itself. Now you have a lot of simulators, lot of frameworks like, let's say, Mujoko Playground, which gives you a fair starting point of how you can train your models, where you can train your models, how you can bring those into real, and making sure that all these fancy things which looks like a fairy tale come to real life. And these open source simulators did help a lot in researchers to come up with fairly better ideas also. And one more amazing thing is that day by day our physics engines are getting better. We are getting a lot of better, dynamically better physics engines which would not just approximate real life scenarios, hoping to exploit accurate uh, real life physics too. And talking about recent advancements, one of the most important research papers in this field, rapid motor automation, paved the way of what if instead of just randomizing everything in the simulator, what if we just let the robot run in the real world and then let it adopt like how a baby learns. Like we as humans also, we fall when we learn to cycle, and then we learn how not to fall. We don't learn how to cycle, we mostly learn how not to fall off the cycle. So this was kind of the basic idea behind RMA, where they tried to come up with an architecture which would learn to infer the dynamics on the go and then would adapt to it, rather than trying to show every single possible case study in the simulator. So this has two components. One is base policy, the policy which we train for it to walk, and another called adaptation module, which would try to estimate the current state and would try to match it with available data, so that even when there is a change in terrain which was not exposed to the robot earlier in the simulator, it would be able to fairly uh, exploit the existing knowledge and take necessary actions. And the combination of these components enable the robot to adapt to novel situations. I'll also be showing you a video of how they learn to walk in a very dynamic environment. And this is trained completely in simulation without any domain knowledge. Yeah, so the paper didn't use any reference trajectories or food trajectories, and this was also deployed on a real robot. So this was not just a simulator thing. This was a sim to real gap closed, and without any fine tuning. So this was like direct deployment, and this happened with the help of latent variables, which we have discussed earlier, where there will be a fair reduction of dimensionality of your observation space in the simulator, and your real life you will have an estimator which will try to estimate with the available data, and it will try to match it into a latent variable which would fairly approximate your current state and give you desired action. So this is a video of RMA, and I've shown one particular result of this experiment, which is walking on an oil in a plastic sheet. The authors claim that they did not show this case to the robot in the environment, but you could see that the robot was fairly good enough in a lot of varying terrains. Here you could see different terrains with different friction values, different heights, and still you could see that the robot does not struggle and is fairly good enough with the estimates. Yes. Moving to the end of the talk, what are the current open challenges present in legged locomotion, which would bring us closer to a real life robot that is good enough as a real life robot dog. So even though RL locomotion has robustness in what they have shown earlier, it is not as robust as an animal is in real life. And efficiency is of course an issue. It consumes a lot of power. You need a very good torque levels in motors, and one major challenge in my own opinion is generalization issues. Till now we don't have a solution, a policy that is good enough so that you could have just shown one robot, one morphology, the policy, and you take you take the policy and put it in another robot, and it just works. It works out of the box. It's like a human brain which has tried to learn the essence of locomotion rather than trying to learn locomotion for one specific hardware or one specific morphology. And second is, of course, high training time and compute requirements. Even with better GPUs, we are actually facing we are still facing high training times and policies, and that would obviously cost you in coming up with solutions and thinking about the next steps. And even though multi-terrain, multi-gate, and multi-robot policies do exist, there is not a benchmark level policy yet. Our RMA was one such policy, but something which is good across all this at the same time. And one last thing is the current algorithm which we use, PPO, still need a large amount of samples, fairly large amount of samples and online interaction with the simulator. But what if there is a algorithm that could learn the essence of locomotion with a fairly low amount of sample. So, and one of the major challenge that is still yet to be solved is an accurate simulator, a simulator which is good enough, not good enough, a perfect enough estimation of real world. That is still an unsolved problem. You can only approximate context. Still, you cannot accurately model context. It is hard to induce hardware wear, the different calibration and everything. And safe exploration in robots is still difficult. Yeah, let's say you're doing sim to real, there is still no guarantee that you wouldn't break your robot. As long as you know what actions you're taking and whatever you're doing is a fair safety measure, but still predicting that safety component is still a challenge. And even with a lot of world models, offline data sets, and all such resources, we are still far away from one policy for many morphology and terrains. So, trying to summarize the whole talk, we did talk about the classical control way of legged locomotion, reinforcement learning inside simulation, and the progress of RLN simulation in parallel with the progress with your policy gradient algorithms. And we did also discuss the issue of sim to real on quadruped robots. We also did discuss about how multi-terrain locomotion is possible with control settings, not fairly, not a fairly on the go thing, but you still have major challenges of generalization and sampling efficiency in your locomotion policies. So, concluding the talk, I would like to thank uh, Reward Loop for giving me opportunity to talk about this. And we in IIT Jodhpur, we are working on we are building a quadruped robot here at our labs. So I would like to take this opportunity to present you, to take a few minutes of your time to present you the works that we have done till now, the progress. So this is our website where we keep on updating the resources as on the go. And we do have a Deep Robotics Lite 3 robot in the lab. And we are planning to implement all these state of the art policies and test and try to research about how good it would be to come up with a one-off policy. We are also building a robot on our own. You could see this is the leg design that we are trying to do. We are trying to build a prototype first, which could be a fair enough uh, estimator for us to run policies, because the resources, the motors that we are using for these robots are really bad, like really like a lot of backlash, and these are not high level motors. So I think if we could model this and come up with a policy that is good enough for motors like this, we believe that we could come up with a fairly working estimate for better robots. And these are your simulation environment. So we work with Mujoko as a simulator. We are using Mujoko Playground, an open source framework by Google DeepMind for training our policies. And we are yet to do Simtorial though. We haven't performed Simtorial yet. And if you are interested in working with us, sure, you can text, ping us, send an email, or we can even collaborate to have fruitful discussions about the topic. Yes. And I hope this was one of session where you got a fair basic introduction to advancements in legged robots. Yep. Thank you.
Thank you, Vishwanath, for the insightful talk. Now I open the floor for discussions. I would request all the participants who have any question to unmute themselves and ask any questions if they have. Okay, so I will start with a question. Vishwanath, you showed the RAM
RMA.
experimental video.
Yes, yes, sir. Yes,
Uh, you specified particularly the one where it was moving on a oiled surface.
yes, sir. Yes,
Now, we generally, if we are moving over a oil surface or a puddle, or say if a cat moves over it, it will try to avoid the surface as much as possible,
correct.
or
True,
to move, or to try to avoid from the say heaviest pool of the oils.
true.
Now, uh, why does not this robot do it?
So one fair reason is that this does not use exteroceptive data. So basically, when to find that there is a very large amount of oil pool in one area, you of course need something like a camera data to avoid it at the first, right?
Right.
When you are using data from proprioceptive sensors,
Mm-hmm.
and when you find that you enter into a region of, let's say, a large amount of oil, you
Mm-hmm.
can still see that the robot's leg is far enough to tackle the section, and of course it doesn't avoid it, but it makes sure to go into places where probably it will try to exploit to go into places where it doesn't slip off. And the main objective of this RMA was not to avoid such scenarios. It was to adapt to such scenarios. Like, even though you are exposed to a place, like let's say you are exposed to a place where you have such things, how would you balance the robot? Like, how will the robot learn to balance itself?
Mm-hmm.
Maybe integrating exteroceptive data like camera data, like trying to identify that the density of oil at this region is larger, would
Mm-hmm.
of course add on to the policy to make sure that it doesn't end up falling there. Probably it will fail in that region, so it will try to avoid it, but with proprioceptive data it is hard for you to estimate that beforehand, right? So that is the reason why RMA probably doesn't do that.
Right. Another thing is, we generally have the one part is we want to make it as general as possible to adapt it
True.
to as many surfaces as possible. Now, the
Yes.
application maybe one is say household robot, right?
Yes. Yes.
But say if we look at machines, if I'm talking about say industrial robot, do
Yes.
you think that the generalization is as much required? Because when we talk about industries, we have been say since 100, 150, 200 years since the industrial revolution, and we try to build particular machines for particular tasks which does that particular job beautifully, instead
True.
of making machines which do all the things.
Yes.
So do you
Correct.
think these randomization or say adaptation technologies would be useful much where it is working in say humanly environment or outside world instead of industries?
Uh, in my own opinion, I believe that if you are very sure about the task of what should be done, then I
Hmm.
think at those places, uh, task specific or task tuned policies
Right, or traditional
could be,
controller, I think would be
yeah,
better.
could be more beneficial.
Hmm.
But what would make such things easier is that if you have an underlying generalized policy which can later be fine tuned to one such task,
Hmm.
that I believe would be uh, more like accurate, or I don't know the exact word, appropriate for the
Hmm.
task than a fine tuned task. Because maybe if you learn a policy which is good enough only for that task,
Hmm.
and later if you are trying to like add something new into the environment,
Hmm.
there is a need for you to fine tune the task. Like there is a need for you to retrain the task again. But fine tuning a policy is more of a easier, like more of a good thing to do with the generalist policy rather than trying to learn it for one task again and again.
Right. Right.
And the
Thank you.
issue with traditional thing, maybe, is that we need to invest a lot of time in engineering values. And of
Right.
course, yeah, we
That's
all know it better. That's a very
hmm.
a time consuming task. So I
Yes.
think with deep learning, maybe neural networks being learned to fairly estimate all those things, I think it's better to exploit them along with traditional controllers rather than trying to have pure traditional in those spaces.
True. Right. Thank you. So, anyone else, if they have any question? Mr. Sai Kumar Reddy,
Hello,
do you
sir.
have any questions? Yes.
I'm not really familiar with this topic, so I'm just curious about
Fine.
the adaptation, the rapid motor adaptation algorithm.
Oh, do you want me to explain it again, or
Uh, no, no, like, how is it different from, say, like traditional adaptive control?
so the how you could explain it in a way is that uh, the adaptation module present in the RMA would actually try to guess your environment. So rather than trying to come up with an accurate representation, so basically assume that it has a dictionary. Like let's say it has a dictionary of key and value pairs, right? Like if this is the state, this is the action. If this is the state, this is the action. So
Yeah.
what it will try to do is it will try to take the sensor data, and then try to come up with like putting it in a layman terms. Let's say it comes up with a fair number, and it sees which number is closer to the index that you have in the dictionary, and whatever is in approximately good region, you take that action. And they have shown that it's not that they don't have domain randomization in the environment, they do have it, but they showed that it's not necessary for you to show every single possible environment in the real world. And how is it better than traditional adaptive controllers is that the work required for a human to to teach all those things to that controller is much less compared to what you do with traditional controllers.
Thank you.
Yep, thank you.
Thank you.
And
Uh,
you can also refer to the paper website if you have doubts about it. This is the paper rapid motor adaptation for legged robots. Maybe if you go to their paper, they'll have they do have a website which shows the uh, which explains it in much detail.
Yeah, yeah. Thanks.
Aditya, do you have any questions?
Uh, can you repeat this part where you have explained this uh,
Where I've explained.
privileged observation to the
Oh, so okay. So in privileged learning, what you do is that so you will in the simulation you will show policies, states which you cannot extract from real life too. So it's basically giving it extra cheat code data, not a cheat code data, extra information about every possible data available for it to extract, which might not be available in real life too. So you train this policy in simulation, and this is on one side. And then in the real roboting, the student policy would be trained with the observations which are available to the robot in the real world. So some major examples are terrain geometries, because it's hard for you to get accurate terrain. It's hard for you to get terrain geometry data itself in a real life robot. So you would have an action, you would have a prediction of action for the student policy. You will also have a prediction of action for the teacher policy, and you would try to minimize this loss. So this knowledge distillation method is what you do in privileged learning. This is like one way of privileged learning, and the other is the latent variable approach, where you try to reduce this higher dimensional data into a lower dimensional data, and you will also have a estimator in the real robot, which will also predict a lower dimensional value, and you'll try to regress these values, and that will give you a fair, approximate, or accurate action that could be taken.
Thank you.
Yeah.
Okay, thank you, Vishwanath, for your talk. I will also take this opportunity to invite anybody of you to present in the next talk, if you would like to. You can also mail to us, or visit the website and contact us through there if you would like to present in the next session. With this, I would like to conclude today's talk. Thank you everyone for joining. We will see you in the next to next Saturday. Thank you. Have a good day.